Hello everyone. What we're doing today is we're having a look at the KS test, the first test in our comparative test sequence that we're doing over the next 3.5 weeks or so. So I just want to go through this one test just as an example of the kind of coverage that we'll have for each one of the tests coming up. So the essential questions that we want to answer today are: what is this particular test and why use it? And a little bit of insight into how we use it in terms of case study examples. So the KS test itself is in full, the Kolmogorov-Smirnov test of goodness of fit, but we normally just call it a KS test. So the idea here is that we compare an observed data set, actual empirical data, with any other probability distribution. So that could be a theoretical distribution created by a model, or it could be another empirical distribution created by observation, let's say in a different place, and we're just looking for the goodness of fit. How well do they fit each other? So it's non-parametric, does not assume any particular distribution, but it does require ordinal data. So there may be a data transformation that's necessary if you don't have data in an ordinal form. So the KS test itself is commonly applied as a test for normality to see if your data set is normally distributed. So this addresses that issue that we came up with earlier, where we had an empirical data set and we were trying to determine how well it fit a normal data set, and so we were able to create a theoretical distribution that fit the characteristics of the empirical data set broadly, but we wanted to see, is the empirical data set actually normal, yes or no? So as we're beginning here, let's just check out a simple example to get a basic idea of how the KS test works. And we'll focus on rainfall as our example. So in column 1 we've got our classes in millimeters, so 10 to 20, 20 to 30, etc. These are the division boundaries, the class boundaries. Column 2 is the observed frequencies that we actually observed in each one of those categories. Column 3 is the observed probability, so converting those frequencies into a probability. And then column 4, probability if the data were perfectly normal. So it's got the same mean and the same standard deviation as the observed distribution. But the thing with column 4 is that it's created as a perfectly normal curve. So we're just trying to see if the observed, again, fits that perfect normal distribution. So again, this came up in week 3 when we were discussing this before, if you're looking for more insight into what we're talking about there. So the idea here is that we would cumulate or add up both of our columns 3 and 4 as part of the KS test process. So here's the cumulative observed probability from the empirical data that we've got. So we're adding up consecutively each observation until we get to 1.00 or 100% of the data. And then we accumulate the normal probability, that theoretical curve that we derived, and we get to those numbers right there. Now the task with the KS test is to calculate the column differences at each step along the way. So the corresponding same class differences. So you can see how we're doing that. 0.17 minus 0.11, 0.40 minus 0.32, etc., etc., as we go through this. So we end up with a column with the differences, and we're searching for the largest difference in the column. And that is our KS test statistic D. So in this particular case, the largest difference is 0.15, and so that is the value of our statistic D. So actually a pretty simple methodology for completing the calculation not really a formula. It's more a process to get to the end that we need. Then we can go to our KS test statistic D critical value table, and we observe that the number of items in the observed frequency distribution is the degrees of freedom. So we need that. And in our particular case, n equals 30 for the data set that we've just been dealing with. And then, of course, we need to select our desired level of significance. So to complete the 6 steps we've got that we just talked about in class earlier: null hypothesis, alternative hypothesis. We know it's a KS test that we're doing. We're going to select significance level 0.05. Now, of course, we're a little bit out of order here because we actually already do have our KS test actual value determined, so we're breaking the rules here. But just to run through the 6 steps, here we are at step 3, significance level. D critical from the table, using that information with the degrees of freedom equals 30 and a level of significance of 0.05. We see the D critical at that particular level, 0.240. And we already know that our D observed is 0.15. And now we go to make our decision. Since D observed and D critical are determined, D observed is less than D critical, so we can accept our null hypothesis. Thus, the KS test indicates the sample is from a normally distributed population at the 0.05 level. So that's kind of following through the whole way. So let's pursue this stream and tributary example. This is another variation on the possibilities of application for KS test. Want to emphasize KS test is applicable to all distributions, so we could be comparing an observed situation versus a modeled situation. Maybe we've got a model that provides us with a prediction, an expectation, so that's where we're going here. But also we could mention that KS test can compare an observed distribution with the historical record. So we're not even talking about a model in that particular case. We're just seeing if, let's say, a current data set differs from the historical record. Is there a change that's evident in what we've just observed with the long-run historical norms? So that would be an interesting one as well. So that would answer this kind of question: was this year significantly warmer than a specific past year or historical averages? But where we're going here is comparing an observed distribution with the predictions of a model. Observed versus model. So in this example, is the distribution of tributaries along a river random? So random, in this particular case, we're looking at the coincidence with the Poisson distribution. So we know that the Poisson lines up with random. So not random, no coincidence with Poisson. Therefore, there is some ordering mechanism that could be modeled. So is this a random situation where basically we don't have any interest in doing further research, or is this a situation where no, there's some kind of pattern, and so there would be some worthwhile effort put into modeling that? So we're testing for Poisson distribution, the null hypothesis being Poisson or random, with the alternative being not Poisson, not random. So that's the basic idea here. So here's the situation in case you're having any kind of challenge understanding what we're getting at. Is the distribution of tributaries along a given river random? So we've got the main river in this map, and along the main river we've got tributaries 1, 2, 3, etc., all the way up to tributary 20. And we're wondering at the spacing of those tributaries along the river. So the river channel itself is 20 kilometers long that we're measuring, and there happen to be 20 tributaries that are feeding into the river along that length of river. So is the distribution of tributaries along the river random? number of tributaries in a kilometer, 0, 1, 2, 3, 4, so those are our classes. The frequency, where we've got 0 tributaries in a given kilometer, 7, 1, 9, 2, 3, etc., etc. So we've got our empirical data, and then our observed probability, just converting that to a probability. You can see that there. The Poisson probability, the random, we can calculate that again with the same mean and standard deviation as in the observed data set. Is there a fit there? And then what we can end up with at the very end, doing that simple difference calculation at each stage, the difference in the cumulative probabilities. So we're combining a couple of things here. We're accumulating, and then we're looking at the difference, and there we go. But with that in place, with that general process in place, following the 6 steps, null hypothesis, alternative hypothesis, as we've stated, we're using the KS test. We're setting a significance level of 0.05. We know our number of observations, and so our D critical is equal to 0.294, looking that up from our KS test D critical table. Our D observed, we're just seeing from the data, is 0.06, and therefore at the end, because we know our D critical and D observed is less than D critical, so we accept our null hypothesis, and we state with statistical confidence at the 0.05 level that the tributaries spacing or distribution along the river are random. So that concludes just a brief tour into the KS test. So it gives us an idea of the calculation of the KS test, and it gives us concurrently a couple of examples of the application of the KS test. So if you ever have a situation like that fits those characteristics with an observed empirical frequency distribution and some other form of frequency distribution that you want to have a look at whether or not they coincide, the KS test would be a good way to go. And so next week what we'll do is we will go even further into this multi-week survey of comparative statistical methods with a couple more. Mann-Whitney-U, which we haven't encountered yet, and then Students T that we've seen a little bit in action, and we'll cover more thoroughly next week. So thanks for being here. Appreciate you watching the video. I will see you in class. Take care.